Welcome to the fourth Frederick Reines Lecture. My name is Ken Janda, and I'm lucky to serve as the Dean of Physical Sciences here at the University of California, Irvine. And tonight we're really honored to have Kip Thorne, 2017 Nobel laureate, to teach us about gravity waves. Thank you, Kip, for making the trip down. It's great to see so many of our alums and supporters, students especially from local high schools and middle schools who want to learn a little about physics. Frederick Reines was UCI's founding dean and was the recipient of the 1995 Nobel Prize for the observation of the neutrino. Fred's words of wisdom, that's become our school model, were never stop asking why. Since its founding, the UC Irvine School of Physical Science embodies this spirit. We ask the really hard questions, and through visionary, interdisciplinary research, we deliver the answers. We catalyze breakthrough solutions and insights to some of our time's most existential challenges: human disease, climate change, and advancing humanity through a deeper understanding of the world around us. Faculty and students in the Department of Physics and Astronomy continue to be at the forefront of their fields and to share the department's rich history. I'd like to introduce Chair of the Department, James Bullock. James is a theoretical cosmologist who studies galaxy formation. He attended The Ohio State University and the University of California, Santa Cruz, where he was awarded the PhD degree. After a postdoctoral stint at Harvard, he joined the UCI faculty in 2004. Among his many honors and awards he's a fellow of the American Association for the Advancement of Science and a UCI Chancellor's Fellow. His research has been featured on BBC News, LA Times, Science Magazine, Discovery Channel, National Geographic, the Science Channel, and How the Universe Works, and other prominent shows. James.
Thanks so much, Ken. It's really a great pleasure to be here and welcome you all to the fourth annual Fred Reines Lecture. Fred Reines, as we just heard, was the founding dean of the School of Physical Sciences. And before introducing tonight's speaker, Professor Kip Thorne, I'd like to give you a little background on Fred Reines and then tell you a little bit more about what we're doing here within the Department of Physics and Astronomy right now. As Dean Janda mentioned, Fred Reines is famous for discovering a brand new elementary particle of nature, the neutrino, and for this, he won the Nobel Prize in Physics in 1995. Now, the idea of the neutrino had actually been around since 1930, when Wolfgang Pauli proposed its existence to explain a puzzle. The puzzle had to do with radioactivity, and when nuclei decay, they spit out radiation, and this radiation was missing energy. And what Pauli suggested was that this energy wasn't really missing. It was being carried away by this new particle, this neutrino, that was just incredibly hard to detect. Now, this neutrino it had to be so weakly interacting that in fact it could pass all the way through the Earth without being stopped by anything. It was a ghost. And Hans Bethe famously proclaimed that it was impossible to detect this thing. Pauli himself bet a case of champagne that no one would ever detect it. Enter Fred Reines. Together with his colleague Clyde Cohen, they set out to do the impossible, and they built an experiment that did just that. It detected neutrinos coming from a nuclear reactor. This was the man who founded our school. He was creative enough, a little bit stubborn enough, and hardworking enough to do this thing that other people said could not be done. And let me tell you that spirit is alive and well within our school and within the Department of Physics and Astronomy today. Physicists within our department are continuing to try to unlock new cosmological mysteries. One of them, for example, has to do with dark matter. Dark matter is another theoretical particle. Dark matter, in fact, is so weakly interacting it makes the neutrino look like an extrovert. Within our department, astronomers are working together with particle physicists to scan the skies and smash atoms to try to figure out just what this dark matter is. Still others within our department, condensed matter physicists, are working to bring about the next technological revolution by developing quantum computers and build molecular scale electronics. And others are working on ways to desalinize seawater and to stop harmful bacteria from infecting cells. One more tidbit, you may not know this, but the world's largest and most advanced private fusion energy company in the world was founded on ideas developed right here at UC Irvine by Norman Rostocker, who was a contemporary of Fred Reines. Fusion, of course, is what powers the sun. And ideas on how to make it work here on Earth, developed here at UC Irvine, are now being utilized to attempt to produce carbon-free, uninterrupted power generation that could one day power the world. So now on to tonight's speaker, Kip Thorne. Now, Professor Thorne perfectly honors this legacy of Fred Reines. In 2017, he was awarded the Nobel Prize in Physics, along with Rainer Weiss and Barry Barish, for his contributions to the development of the LIGO detector and its observation of gravitational waves. But not only has he done fundamental prize-winning research in astrophysics and physics throughout his entire career, but he is also among the most successful and important teachers of scientific ideas alive today. Most professional physicists, myself included, learned general relativity from his famous textbook, Gravitation. More recently, he co-authored a new textbook on modern classical physics that I suspect is motivating departments across the globe to rethink how they're teaching the subject. As you'll soon see, Professor Thorne is also a gifted popular communicator of science. He was an executive producer of the 2014 film Interstellar. Now, if you don't remember this movie, officially it starred Anne Hathaway and Matthew McConaughey, but the real star was a wormhole. If you want to learn more about wormholes and the science of interstellar, I strongly suggest you check out Professor Thorne's book about the science of interstellar. Now, as we're about to hear, one of Professor Thorne's many contributions to basic science was developing the ideas that led to the detection of gravitational waves. Now, one of the reasons why this was really important is that by detecting gravitational waves from distant astronomical objects, this opened up a brand new window into the field of astronomy. Historically, astronomers have always relied on basically light. So even the first astronomers who looked up at the sky were studying stars with the light coming from them. Today, we study all kinds of light, electromagnetic radiation, X-rays, gamma rays, microwaves, but ultimately, it's always been electromagnetic radiation. Thanks to LIGO, there's a brand new thing, gravitational waves. We're entering a new era of multi-messenger astronomy that allows us to hear or see, or possibly you might say hear, the universe in an entirely different way. Now, Fred Reines would have loved this development. One of the last experiments he led here at UCI actually detected neutrinos coming from a distant supernova that blew up in 1987. Today, researchers within our department are working to construct a new neutrino telescope called Ariana on the surface of the cold, transparent ice in Antarctica. The hope is that one day we'll be able to study the same explosive events from deep space using neutrinos, light waves, and yes, gravitational waves. But of course, this will be in the future. Before then, I invite you to sit back and enjoy the fascinating story of gravitational waves from the Big Bang to black holes by our 2018 Fred Reines lecturer, Professor Kip Thorne.
Thank you. It's a great honor to be here and give this lecture. I came to Caltech on the faculty before almost any of you were born, 1965, or 66. And 1 year earlier, in 65, I believe, was when Fred started to build the physical sciences division here at UCI. I had a collaborator here who was on the faculty in 1966, 67, and so I came down to Irvine quite a bit to work with him on research, working on the theory of pulsations of relativistic stars, neutron stars, and so forth. And I watched the early period of the building of this great institution in the physical sciences and admired Fred's work on that, and then cherished him as a colleague through the subsequent decades as UCI grew stronger and stronger And I had then further collaborations and interactions with people here, such as Joe Weber and Virginia Trimble, who were not only dear colleagues, but dear friends. So it really is wonderful to be here to give this lecture. And I would like to begin with a little story that 1.3 billion years ago, if we can turn the lights off, when multicelled life was just forming on Earth, but in a galaxy far, far away, two black holes orbited around and around each other, creating ripples in the fabric of space and time called gravitational waves. This is what they would have looked like if you had been up there looking with your own eyes. They create the spiraling pattern in the stars behind them through a phenomenon called gravitational lensing, the bending of the starlight as it goes around and around the black holes. The black holes collided, as you just saw, merged, and in that merger, they created a gigantic burst of gravitational waves that went traveling out of the galaxy in which those two black holes lived into intergalactic space, across the great reaches of intergalactic space, and reached the outer fringes of our galaxy, the Milky Way galaxy, 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. Just think of that. Moved onward through our galaxy for 50,000 years, and on 14 September 2015, they arrived at Earth. They arrived actually initially at the tip of the Antarctic Peninsula. These waves traveled up through the Earth, just like neutrinos penetrate through the Earth unscathed. Gravitational waves do as well, and emerged at the LIGO, that is the Laser Interferometer Gravitational Wave Detector in Livingston, Louisiana, and 7 milliseconds later, 7 1,000th of a second later, they arrived at and emerged from the Earth at the detector in Hanford, Washington. The LIGO team of 1,000 people analyzed the data for a period of several months, trying to be absolutely sure that what we saw coming out of our detector was a signal that really was due to gravitational waves. These are a few of the 1,000 members of the LIGO collaboration that worked on this, plus several hundred people from the Virgo collaboration in Europe. Finally, on I guess it was February 12 of 2016, the discovery of the gravitational waves was announced, and it made headlines in all of the major newspapers around the world. For example, the New York Times here with a photograph of the vacuum tube in which the laser beams go back and forth as part of the LIGO experiment, and a headline with a faint chirp, "Scientists prove Einstein correct, they've discovered gravitational waves." Almost immediately, this discovery seeped into popular culture. For example, Ray Weiss, my collaborator, was on a subway 2 days later in New York City and saw this, and this is an actual photograph that his son-in-law, who was with him, took of two people on the subway, typical New Yorkers. And this says, "Scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet." And the day after the discovery was announced, in the New Yorker that came out on that day, a cartoon, two birds sitting on a branch. The sound of the gravitational wave, if you were to put it on a speaker, is that of a chirp. And he says, "Was that you I heard just now, or was it two black holes colliding?" So how did we get here? And I'm going to change batteries. My battery is already going out. Fortunately, I did bring some more. How did we get here? I'm going to tell you the story in brief from my own personal perspective. Just give me a moment. I thought I had fresh batteries in there, but I didn't. My story begins with Albert Einstein. A little over 100 years ago, Albert Einstein predicted the existence of gravitational waves. He had just formulated his theory of gravity, called general relativity, and he used the equations of his theory to make this prediction, and he told us that there should be these waves that travel across the universe, and that their physical manifestation is that they stretch and squeeze space. What that means, in more technical terms, is if you have two inertial reference frames, one here and one there, as the gravitational waves goes by, the inertial reference frames move back and forth with respect to each other. That means that if you have two particles that are sitting one here and one there, as the waves pass, the particles always try to remain inertial, so they're pushed back and forth with respect to each other. But there's a stretching along the horizontal direction if the waves are propagating into the screen, while there's a squeezing vertically, and then when there's a stretching vertically, there's a squeezing horizontally. And so that's what the pattern would look like if the waves went through a set of particles. Now, Einstein wrote a technical paper describing these gravitational waves in 1916, just 100 years before we announced the discovery of the waves. And he said in that paper, these waves, for any phenomenon that occurs in the universe, he said in effect, it wasn't quite in these words, these waves will be so weak that humans are unlikely ever to detect them. However, Joseph Weber at the University of Maryland, beginning about 1958 or 59, but most of his work done in the 1960s, built a gravitational wave detector. He was the first person to have the courage to do this and to figure out a way to do it that might have a possibility to succeed. And why did he have the chutzpah to do this when Einstein said it was impossible? Basically because there was new knowledge. I don't think knowing Joe really well, I don't think it mattered to him, but it did matter to me that there were now sources of gravitational waves that you could believe might be detectable, black holes and neutron stars, which were unknown in Einstein's period. But for Joe, the important thing was that there had been major developments in technology, such as lasers and computers, new technology that enabled him to have new tools that Einstein never dreamed of to do the experiment. Now, I spent 2 months in Les Ouches in the French Alps in 1963. And Joe lectured there at Les Ouches about gravitational waves. I was a student, and I listened to his lectures, and then I went walking with Joe in the French Alps, talking about gravitational waves and the experiment that he was developing. And I basically became a convert, that this was really exciting. Gravitational waves would be wonderful if they can be detected. And so, largely inspired by Joe on the experimental side, and then on the theoretical side by my PhD advisor, John Wheeler, and a few other theorists, I decided that I wanted to pursue gravitational waves as one of the fields in which I worked when I moved to Caltech on the faculty in 1966. And yes, that's me. The hair moved off of my head and onto my chin. So I built a theory group beginning in 1966 where we worked on black holes, neutron stars, and gravitational waves. And we began to develop a vision for the science that might be done with gravitational waves if they could be detected. And the key thing that underlay this vision is the vast contrast between the electromagnetic waves with which astronomers normally study the universe, light being the primary version, and gravitational waves. Electromagnetic waves are oscillations of the electromagnetic field that propagate through space-time, while gravitational waves are oscillations in the fabric or shape of space-time itself, as I have described. Electromagnetic waves in astronomy are almost always incoherent superpositions of emission from individual particles or atoms or molecules, whereas gravitational waves are coherently emitted by the bulk motion of matter, or more precisely of mass and energy. Electromagnetic waves are all too easily absorbed and scattered as they travel across the universe by matter. Gravitational waves are never significantly absorbed or scattered, not even if they are created in the birth of the universe, near what we call the Planck era. And these extreme differences have some important implications. First of all, many gravitational wave sources won't be seen electromagnetically because the emission processes are so different, the penetration is so different, and so forth. And second, enormous surprises we felt would be likely if gravitational waves could ever be detected. And so it was clear to me by 1972 that this was really the most exciting thing that I could work on if the experimenters could really pull it off successfully. Now, Joe Weber published a result in 1969 announcing evidence for, he didn't say he had discovered gravitational waves, but evidence for gravitational waves. It turned out that he was not seeing gravitational waves in the end, but nevertheless he got everybody else in this field going as an inspiration for us, and he also developed much technology and some data analysis techniques that underpin what we do today. So we regard him as the pioneer of our field. Ray Weiss was another pioneering figure. Ray, in 1972, April 15, 1972, he published in an internal MIT technical report the idea for and an analysis of the kinds of gravitational wave detectors that we would ultimately use in LIGO for detection of gravitational waves. He had mirrors that hung from overhead supports. You're looking down on this diagram. And laser beam that would go in, get split in half, and go down and bounce back and forth many times between these mirrors. The same thing between those. Laser beam would come back, recombine, and when these mirrors moved apart and those moved together, there would be a change in the different distance that the light in this arm traveled compared to that arm. And as a result, through the interference of the two light beams, the intensity of the light going down here to a photodetector would increase and decrease in just precisely the pattern that gave you the shape of the wave that is passing. So this was his idea. But the remarkable thing was that Ray then identified all the major noise sources that the first generation of our LIGO gravitational wave detectors would face, described ways to deal with each and every one of them, and estimated then what kind of sensitivity could be achieved with such a detector, and concluded by comparing with the strength of the waves that I and my other theorist colleagues were predicting, concluded that if you made such a detector that was a few kilometers long, you might have a serious chance of success. Now, I heard about this. I had not yet studied Ray's paper. Well, first, it wasn't published in the regular literature because Ray, being Ray, had the attitude that you don't publish something like this until after you've built the instrument and detected gravitational waves. And so, but he did disseminate it to his colleagues. But at that same time, and before I saw a copy of this or had had any serious discussions with him, we were finalizing the text of our book, Gravitation, the textbook that I co-authored on relativity theory. And so I looked at the basic idea, I looked at some numbers, and it was obvious to me that Ray was crazy or stupid or something. And so I used very gentle words in this textbook. I wrote a sentence which said, "This idea is not promising." And I wound up eating crow. I spent about 60% of the energy of my whole career trying to help Ray and the other experimenters pull it off afterwards. But why did I regard this as crazy at the time? Well, just look at some numbers. You're trying to measure the motion of two mirrors using light. And I'm going to tell you how big the motion of these mirrors is that you have to measure. Let's begin with 1 centimeter, which is just a little smaller than an inch, of course. You divide by 100, you get the thickness of a human hair. Divide by 100 again, you get the wavelength of the light that is being used to try to measure the motions of the mirrors. Divide by 10,000, you get the diameter of an atom. Divide by 100,000, you get the diameter of the nucleus of an atom. Divide by 1,000 again, you get the magnitude of the mirror motions that we thought you might have to be able to measure in order to pull this off. And I looked at those numbers and I said, Ray is crazy. This is 1 trillionth, 10 to the minus 12, 1 trillionth, the wavelength of the light that Ray is going to use to make this measurement. In technical terms, you're going to split a fringe by a part in 10 to the 12. I mean, this is obviously not possible. And then I studied his paper in detail. I did some more serious calculations. I had extended discussions with Vladimir Braginsky, a dear friend, physicist in Moscow, Russia, and with Ray, and I became convinced that it could succeed. being convinced, I decided that I, as a theorist, would do everything I could to help Ray and his experimental colleagues pull this off successfully. At about this time, and a few years later, I guess it was probably 2 years or so later than the beginning of this story with Ray, Ron Drever in Glasgow, Scotland, had a brilliant idea for an alternative way to bounce the light back and forth in the arms. I think Ray recognized before this that you could do it this way, but it was only Ron who really identified that it was possible to pull it off technically and that would have some very, very big advantages over Ray's way. That is to bounce the light back and forth, fold it onto itself by making these mirrors be the mirrors in a resonant cavity, so the light resonates back and forth upon itself, building up coherently a very intense beam in here. And that kind of a technique then turned out to have great versatility and great power. Although it was harder technically to pull it off, it is fundamentally simpler and more powerful in the end in the modern era. 1976 to 1978, I talked to my colleagues in Caltech and said, we really ought to get into this game. We should build an experimental group to work alongside Ray Weiss's group at MIT, because this is really a very exciting field. My colleagues in the Caltech administration jumped in with both feet with great enthusiasm, and we brought Ron Drever then to Caltech to lead the effort. We also brought Stan Whitcomb, who began as an infrared astronomer. He was a young guy. He had just recently received his PhD. We brought him in to work with Ron in leading this and to be the hands-on leader in building a 40-meter prototype detector of the sort that Ray had invented and then Ron had modified by changing what goes on in the arms of the light bouncing back and forth. In parallel with building the 40-meter prototype at Caltech, Ray Weiss and his group at MIT completed the construction of a smaller prototype gravity wave detector, and they also carried out a feasibility study for kilometer-scale interferometers, costing of them, technical issues you would face in enlarging these to kilometer scale. And on the basis of that, of their feasibility study, the prototype work they did, the prototype work done at Caltech and prototype work done in Ron Drever's group in Glasgow, Scotland, and a group in Garching, Germany, we went to NSF and were encouraged by Richard Isaacson, a superb program director at NSF, to move forward in creating the LIGO collaboration. From 84 to 87, then our collaboration of Caltech and MIT in planning to build these gravitational wave detectors with kilometer scale sizes, it was led by Ray and Ron and me. This was the most dysfunctional leadership you can imagine. It was almost like a cartoon. It was a fundamental issue that although Ron Drever was highly creative, he had difficulty functioning in a collaboration where he didn't have full control over everything he was doing. And there were big disagreements between Ray and Ron about how you would go about things. And I was the mediator. And by the end of 1986, early 1987, it was just clear that this was a disaster waiting to happen. And so we brought in Robbie Vogt to be a single director with the authority to bash heads together and get Caltech and MIT working together jointly, and to lead us in writing a proposal for the construction of LIGO. So under Robbie's leadership, we wrote and sent to NSF in, I think it was November of 1989, a proposal to construct facilities in which we would place the interferometers, and we would then build 2 generations of interferometers, an initial set of interferometers that would be simple enough that we knew how to do it then and that we really were confident we could pull them off, but would not be sensitive enough to have a high probability of detecting gravitational waves. If we were lucky, we would see waves, but we would have to be awfully lucky. Nature would have to be awfully kind to us. But then, with the experience we got with the initial interferometers, we would build a second generation called the advanced interferometers, which should have a high probability of seeing gravitational waves. So that was our strategy in our 1989 proposal, We struggled from 1990 to 1992 to get this funded, and did ultimately succeed in 1992. NSF and Congress bought into this in 1992, and they never turned away from us. We had complete backing from the National Science Foundation and from Congress, regardless of which political party was in power, from then until we ultimately discovered gravitational waves. And I have to hand it to Congress as well as to NSF that I'm impressed by how they stuck with us. But part of that is, frankly, that we told them we would have to build 2 generations in order to succeed, and so they were prepared for our not seeing anything with the first interferometers. When it came time to move forward with the construction and to develop the detailed plans for construction, we brought on Barry Barish, who had been leading the construction of one of the large particle detectors in the superconducting supercollider, which was canceled by Congress in, I think, 94. And so we grabbed Barry and brought him in to lead us through construction and the organization of construction and on through the early interferometers. And Barry was just superb. I think by my judgment, and I think many, many people agree with me in physics, he's the most skilled leader of large experimental projects that the world has ever seen, large experimental physics projects. He led us in constructing the facilities. He organized LIGO, in part expanding it to other institutions by setting up something called the LIGO Scientific Collaboration. That collaboration now has 1,200 scientists and engineers in about 80 institutions in 18 nations around the world. So, because we just did not have, by any means, enough scientists and engineers to pull this off successfully at Caltech and MIT alone. Because these instruments are so complex, there are so many things that go wrong with it that you have to be prepared for, and you have to build into the instruments ways of dealing with everything that could go wrong. And that just required a very large team. He led us through the construction of the initial interferometers and their first searches, and then he left us to go back to high energy physics to lead the design study for the next generation of large particle colliders. And we brought then on Jay Marks and now David Wrightsey to lead our project. The initial interferometers were installed and operated between 2000 and 2010. The advanced interferometers were installed between 2010 and 2015. And now I'm going to pause because I don't want to tell you that gravity waves were detected yet, because I want to go back and pull in a couple of other ideas. In the meantime, on the theory front, there was a very deep issue that Vladimir Brzezinski, the Russian that I mentioned to you, pointed out to us already in 1968. He said that basically, no matter what kind of a gravity wave detector you try to build, you're going to wind up trying to measure the motions of very big masses, human-sized masses, that are where the motion is so small that you will see those masses behaving according to the laws of quantum physics, not classical physics. Let me explain a bit more. In the context of LIGO, you have 2 mirrors separated by 4 kilometers. The light beams bouncing back and forth between them. You're trying to measure in the advanced detectors the motions of 40-kilogram mirrors then to a precision of 10 to the minus 17 centimeters, which is approximately, in technical terms, the half-width of the Schrodinger wave function of the center of mass degree of freedom of the mirror. What that means is that the mirror physically, its center of mass, the thing you actually measure with your laser beam, it's bouncing back and forth, fluctuating in where it is in a manner that is unstoppable and unpredictable. These are quantum mechanical fluctuations. And those fluctuations are at the level that they begin to be detectable by the advanced LIGO detectors at their design sensitivity. And if you go beyond that, you have to deal with that. You have to be able to measure the motion of a mirror that is caused by a passing gravitational wave where the motion is smaller than these quantum mechanical fluctuations. And how the heck do you do that? Brzezinski said, well, look, first of all, you're going to see human-sized objects behave quantum mechanically. He said it has to be possible to build quantum non-demolition technology to deal with this. And so, in fact, much of the work in my own theory research group, in collaboration with Brzezinski's experimental research group, from about 1980 up until the present, has been devoted to conceiving the ideas for and developing the technology for this quantum non-demolition. So this just gives you a sense of the challenges here. And as we go into the future, this is a huge piece of the experimental effort, this so-called QND technology. On the theory front, there was another issue. I expected the first thing we would see would be collisions of heavy black holes, and that is what we did see. But we could not predict what the signal would look like. We could predict while they were spiraling around each other, but not when they were colliding. And the collision waves would be the strongest waves. And so we had to have computer simulations. We had to use computers to solve Einstein's equations during the collision to figure out what the shapes of the waves would be. And then when you saw the waves, you would have to be able to go back to the computer simulations and compare with the computer simulations to deduce the details of the black holes that were colliding. So we had to have simulations. Simulations were not going well because of a variety of very technical problems. And so in 2001, I myself left day-to-day involvement with the LIGO project and devoted my energy then for the next few years to building at Caltech a group doing computer simulations of colliding black holes in collaboration with a group at Cornell that was already going and that I judged was the best group elsewhere in the world. We built what is called the SXS project. I should emphasize that just as I did not build LIGO, similarly, I didn't write the computer code for SXS. All I did was provided some scientific vision for where we were going and judgment as to what kinds of accuracies need to be achieved and things of this sort. So it was really the younger scientists who pulled everything off technically on both the experiment and these simulations. Okay, back to September 14, 2015. The advanced LIGO detectors just gone into operation. They were being prepared for their first search. The first search was supposed to begin about 3 days later. They were just being tuned and brought into the final state. They're very complicated, as I say, and there was a lot of tuning to do, bringing them to their final state to begin the search, when suddenly the first signal came in. So the experimental team froze the state of the detectors. They said, this is the final state. Our search has now begun. And the search then, that first search, continued onward for several months. The first signal that it came in, this is the raw signal with bandpass filtered. So you throw away everything at frequencies below 30 hertz and above about 300 hertz. Because a detector is noisy at those frequencies, you just keep the raw signal in between. This is the signal then, the raw signal, no fancy signal processing in Livingston, Louisiana, essentially the same signal in Hanford, Washington. By then cleaning the signals up and comparing them with the SXS numerical relativity simulations, the simulations are in red, the cleaned up incoming signal is in gray. It could be deduced then through those comparisons that what had been seen was 2 black holes, one weighing 29 times what the sun weighs, the other 36 times the sun's weight. That's a total of 65 solar masses. They collided and they merged. The final black hole only weighed 62 solar masses, 3 solar masses of energy. 3 solar masses of energy had been thrown off as gravitational waves. It's as though you had taken 3 suns and annihilated them completely and turned that all into pure energy and put them all into gravitational waves. And that is what happened in this first observation, the first source. And the distance we inferred then by comparing with the simulations was 1.3 billion light years. So we were off and running. As of now, we have seen 6 pairs of colliding black holes. These are the signals we saw from each of them. The lower the mass of the black holes, the longer the signal lasts in the LIGO frequency band. And so we have signals of various lengths. 36 and 29 solar mass black holes at 1.3 billion light years, 29 and 13 at 3 billion, and so forth and so on, etc. The 6th one doesn't appear here because by that time detection was getting sufficiently routine that the LIGO team didn't bother to put the 6th one on there, but it is playing a significant role in starting to do statistics in order to figure out details of the population of colliding black holes in the universe. It was very important to be able to determine where the source was on the sky so we could look and see if there was any electromagnetic emission. For the first 5 signals, the signal on the sky was very uncertain. The location on the sky was very uncertain. These are error boxes as to where the signals were for each of these. But the signal that came in on August 14 of last year, we identified its location with an amazingly small error box. Well, small, a few times bigger than the moon, but that's small compared to what we were doing. The reason was we now had a third gravity wave detector in our system. It was in Europe. It's called the Virgo gravity wave detector. It was built by scientists in 19 laboratories in France, Italy, the Netherlands, Poland, and Hungary, to roughly 250 scientists. And with then these three detectors, we could triangulate. We determined where the source is on the sky by the delay in arrival time of pieces of the signal at different locations, and that helps us see where the source was. I told you that the first signal came from the south, and it arrived at Livingston, Louisiana, before it arrived at Hanford, Washington. And so that told us the signal was down in the south. We were able to pinpoint it as hitting the Earth near the Antarctic Peninsula. And so if you had three detectors, you could do triangulation a lot better and pin down where it was on the sky. And this turned out to be very important 3 days later, when we saw collision not of two black holes, but of two neutron stars. These are stars that are basically made of pure nuclear matter, that have sizes of diameters, say, of about 20, 25 kilometers, but yet weigh something like 1.5 times as much as the sun. Amazing kinds of stars. The signal, this is a signal in where we plot frequency upward as a function of time. It's called a time-frequency plot. The signal in Hanford, Washington, the little dots in here are noise, but you see the signal sweeping up. This is just a way to visualize the signal. You get much better accuracy on the signal by other data analysis methods, but this enables you to see it visually. In Livingston, Louisiana, and very, very faint in Virgo in Italy. But with those data, it was possible to pinpoint where this was on the sky. It was somewhere in this little error box on the sky. 1.7 seconds after those two black holes collided, or after the signal arrived from the collision, of the two neutron stars, 1.7 seconds after the two neutron stars touched and began to smash each other, there was a burst of gamma rays arrived on Earth, seen by the Fermi gamma ray satellite, and also by an a gamma ray satellite called Integral. And the error box on where that was here, this big error box. It overlapped with the direction to the gravitational waves. And then, looking with X-rays, ultraviolet, optical, infrared, and radio, a signal was seen within a day, suddenly turned on in a galaxy at that location. And so we are convinced from these coincidences of when this happened and where it was on the sky that all of these different forms of telescopes were seeing the same thing. They were seeing electromagnetic waves or gravitational waves from two colliding black holes. This is the beginning of multi-messenger astronomy. Each messenger is a different kind of radiation. What we had seen was something that had been called by theorists a kilonova from two colliding neutron stars. And the theory said that in kilonova you should make, through the atomic nuclei smashing against each other, you should make very heavy elements like gold and platinum, the precious metals. A large fraction of them in the universe should be made through colliding neutron stars. By looking at the details of the electromagnetic emission that was seen from this, is very strong evidence that in fact that is what happened, that there was the formation of these very heavy precious metals in this pair of colliding neutron stars. And also it was possible with this observation, by comparing the gravitational waves and the electromagnetic waves, to measure the expansion rate of the universe with a remarkably good accuracy, not as good as electromagnetic astronomers do by themselves, working very, very hard, trying to pile together lots and lots of data, but with one observation, doing almost as good as had been done by electromagnetic astronomers over the years by very much more complicated methods. So the combination of electromagnetic and gravitational waves is beginning to show its power for astronomy. Now let me show you a few pictures of the advanced LIGO detectors. This is what the detector at Hanford, Washington looks like as seen from the air. The light beams bounce back and forth inside vacuum pipes that are under concrete covers here to protect the light beams from the elements and protect the vacuum pipes from being buffeted by wind and rain and bullets. In the United States, they don't worry about that in Italy. And here is the vacuum enclosures in which the beam splitter sits in here, the corner mirrors sit in there, and this is the size of a human being. And Barry Barish, our brilliant director, chose to put a baseball player there. This is one of the mirrors that's hanging by a fused quartz fiber, a fused silica fiber, and the light beam bounces off of the face of that mirror. It looks colored because of the interaction of light with a molten dielectric coatings that provide the high reflectivity of the mirrors. But I show this just in order to lead up to the statement that these are complex instruments. They have 100,000 data channels coming out of them, telling the experimenters what's going on in the interior of these instruments and in the environment so that you really know whether the instruments are operating properly. But 100,000 data channels, just think about that. That is really a complicated instrument. And that means that these instruments, although they were built to a particular design, there are always some things that are not quite right, and they wind up having a personality of their own that the experimenters must understand after they've built them. And so that is what is going on today. Advanced LIGO was shut down at the end of August, last August. Will not start again until about the 1st of next year. So it's shut down for about a year and 4 months. While the experimenters poke and prod the instrument, try to learn its personality and try to coax it toward the design sensitivity, hoping to get there by 2020 and hoping to make some major progress this year before we start observing again next year. Once we reach design sensitivity, we will be able to see 3 times farther than we have been seeing, roughly 3 times. That means you see a volume of the universe 3 cubed or 27 times bigger. That means instead of seeing roughly 1 pair of black holes collide per month when the instruments are up and operating properly, you see 30 times that, which is about 1 per day or a few per week. So that's where we expect to be in roughly 2020 at design sensitivity. Looking to the future, at design sensitivity, we expect to see not just colliding black holes, but also we see spinning neutron stars that have some deviation from axial symmetry, such as a small mountain on the surface of the neutron star. Black holes that tear apart neutron stars, where the two are orbiting around each other. The neutron star spirals in, gets too close to the black hole, gets torn apart by the black hole. 2 neutron stars colliding, well, we have seen that now. We prepared this slide when we first announced the discovery of gravitational waves, and we had not yet seen this one, and now we've seen it. If we're lucky, we will see gravitational waves from the core of what is called a supernova explosion, where we don't understand very well what goes on in the core. But a combination of gravitational waves and electromagnetic waves and neutrinos are really going to pin down what goes on in supernovae when we ultimately see gravitational waves from those. But that's a much harder target because they're much weaker gravitational waves than the others. And there are bound to be enormous surprises. So that's where we are going. Beyond advanced LIGO, beyond 2020, there are concrete plans now for a modest upgrade called LIGO, Advanced LIGO Plus or A+. Plus a third LIGO detector will be operating in India, which will enable us to get much better all-sky coverage and better localization of where the signal is on the sky so we can tell the electromagnetic astronomers where to go look. And by that point, we should be seeing 1.6 times farther than in 2020, and black hole collisions rates a few per day. Late 2020s, if we're limited only by technical issues and not getting money and not political issues, which is a big if, Then we'll have a third generation operating in the late 2020s, seeing 2 times farther than A+, black hole collisions perhaps once an hour. And then sometime in the 2030s, we're fairly confident we will manage to build a 4th generation of gravity wave detectors that will be able to see so far that you pick up every black hole collision in the entire universe where the black holes are less heavy than 1,000 solar masses. So this is just the beginning of what has happened thus far. And there are other gravitational wave windows, that is, other frequency bands in which we can see gravitational waves. In fact, I expect that by the mid-2030s, we will be looking at gravitational waves in 4 different frequency bands, that is, through 4 different gravitational windows. If you think of X-ray astronomy as being one kind of a window, radio astronomy another, optical astronomy another, gamma ray astronomy another. What I'm saying is that by the mid-2030s, we will have done the equivalent of turning on optical, radio, X-ray, and gamma ray astronomy all over a period of 20 years. And these are all in the works. First, we do have gravitational wave detection with waves that have periods of milliseconds with LIGO, and now with LIGO's partner Virgo in Europe. By about the early 2030s, we will have, we expect, something called LISA, where you have 3 satellites in orbit around the sun that are tracking each other with laser beams and looking for gravitational waves with periods of minutes to hours. The difference between milliseconds for LIGO and these space-based instruments, minutes to hours, that's 10,000 times longer wavelength. And that is the same as the ratio of the wavelength of radio waves to light. So if you think of LIGO and Virgo today as being like optical astronomy, then this is like radio astronomy. And with radio telescopes, you see radically different things about the universe than with optical astronomy. In the same way, we will see radically different things with LISA in space compared to what we see on the ground. Pulsar timing arrays. If you have an array of pulsars, these are spinning neutron stars. That is, they have a radio beam shining off their surfaces, and that radio beam sweeps around in the sky as the stars spin. The inertia of the stars make them have very regular spin rates, which means that as a beam sweeps past you, Earth, time and again, you get very, very regular pulses. And so you can think of these as clocks on the sky sending their ticking rates to Earth. If a gravitational wave sweeps across the Earth, in effect, it speeds up and slows down all our clocks on Earth, and so it looks like all of these pulsars are slowing down and speeding up in unison. And so this then gives us the possibility to detect gravitational waves with periods of years to decades. And then finally, a technique that I will say just a bit about at the very end of the talk, cosmic polarization of cosmic microwave background, can look for gravitational waves with periods of, well, let's say hundreds of millions to billions of years. Now, that's a little longer than the lifetime of a graduate student. And so we're not going to watch these waves oscillate. What you do is you look for a pattern on the sky spatially instead of looking for an oscillating pattern here on Earth. And I will return to that, as I say, at the end of the talk. So those are 4 different frequency bands in which we will be doing gravitational astronomy by the 2030s. I want to conclude my talk talking about some of the science that we expect to do using some of these frequency bands. I'm going to focus on 2 things, basically studies of black holes and studies of the birth of the universe. So let me begin with black holes. A black hole is not made from matter like you and I. Rather, it's made from a warping or curvature of space and time. And this diagram depicts that. If you take a slice, a 2-dimensional slice through the equator of a black hole, and look at its geometry, geometry is not that of a flat sheet of paper. It's not that of what we would call a flat Euclidean 2-dimensional space. Rather, the geometry is highly distorted, and in order to visualize the distortion, we can imagine taking that geometry of that sheet and just embed the sheet in a flat surrounding space. And this is what the sheet would then look like. Near the black hole, it bends down in a funnel like this. The horizon of the black hole is there. It looks like a circle, because I've removed one spatial dimension. It would look like a flattened sphere if I hadn't removed that one spatial dimension. So space is warped in this manner. And then the color coding shows the slowing of time near the black hole. For example, where it's yellow, time is flowing at 10% the rate that it is far away. And down at the horizon, time is slowed to a halt if you're hovering at the horizon and refusing to fall in, which is not easy to do. The arrows describe the dragging of space into whirling motion, or what is called the dragging of inertial frames, with an angular velocity that is proportional to the length of the arrow. So a spinning black hole creates a whirling motion of space that's very much like the whirling motion of air in a tornado, fast near the horizon, slower farther away. Now, LISA, with the three spacecraft tracking each other with laser beams, can look at giant black holes with masses of millions of suns. And one of the things that LISA will do is to map the geometry, the shape of space and time around a quiescent black hole with enormous accuracy. It's like mapping the surface of Mars down to, say, an accuracy of a foot or an inch. I don't know what the accuracy would be in the analogy, but extremely accurate mapping of the geometry of space and time around the black hole. And how this is done is when a small black hole goes orbiting around and around the big black hole, gradually spiraling in the last few years before it goes crashing into the horizon of the big black hole, it sends off a long, long train of gravitational waves that's very rich in its structure and carries the full details of the map. And you can understand why that might be true by just looking at the orbit of the small black hole around the big black hole. I've now removed the geometry of space. I'm pretending that space is flat here just so I can visualize it. And this is then Steve Drasko at Cal Poly San Luis Obispo has made these movies by solving Einstein's equations for the motion of the small black hole around the big black hole as it gradually spirals in. And that orbit does not look at all like the elliptical orbits of the planets around the sun. That orbit is grabbed by the whirling of space and whipped around by the whirling of space. It behaves differently because gravity is not an inverse square law as it is according to Newton. It's affected by the curvature of space. And this small black hole basically explores essentially the entire region of space around the big black hole as it goes around and around, sending off its gravitational waves. And so you have the information there if you can do the data analysis. And so the LISA team, which is preparing for this mission, has shown how to do the data analysis successfully. And what if the central body is not a black hole? Well, here is what the orbit would look like if it is what is called a Manko-Novikov singularity down in here. These are the orbits of a number of smaller black holes going around this central singularity. A singularity is a region where space and time are infinitely curved, but this is a naked singularity, which means it's not inside a black hole. Conventional wisdom, bet that I have had with Stephen Hawking, says that black holes always occur inside singularities always occur inside black holes where you can't see them. There are no naked singularities, but we have the possibility to go to search for them by building a map from the gravitational waves that come off from these objects going around that naked singularity. And you see the inner object, the orbit, is actually mathematically chaotic, it turns out. And the map would be wildly different from the map that you would get if that central object were a black hole. We expect to explore the dynamics of the space-time geometry that are created, the dynamical behavior of a veritable storm in space-time that is created by the collision of two black holes. We do so by building computer simulations and comparing them with gravitational wave observations. So we saw the first two black holes collide back in September of 2015. And the SXS team then did the calculations to compare with the observations and determined just which set of masses and spins of the two black holes correspond to what was seen, what had produced the gravitational waves. And then going back to the simulation, you can see then the warpage of space and time during the collision. So you have the two black holes, each with a sort of a funnel going down here. The red is where time is flowing slowly. The green arrows are the dragging of space into motion. And down here is the actual gravitational wave signal being traced. You notice now I've gone into slow motion, and they're about to collide. I'm going to stop at the moment of collision. This is like a huge splash of a storm at sea. There's the collision. Now it oscillates, and gravitational waves go moving out. And 3 solar masses of gravitational wave energy were carried off by those waves produced by that great splash in the shape of space and time. And those 3 solar masses came off so quickly, in about 1/10 of a second, that the power output during the collision, the amount of energy per unit time, was 50 times larger than the total power output of all the stars in the universe put together. 50 universe luminosities for 1/10 of a second. Just 1/10 of a second. It's very brief, but enormous power. The most powerful explosion that humans have ever had any observational evidence of, except for the birth of the universe itself. Now, this movie captures only a small portion of the space-time storm that's created by the collision of those two black holes. We call this space-time storm the wild vibrations in the shape of space and time, geometrodynamics, a word coined by John Wheeler. I'm going to just give you a little bit of a flavor of what else is going on, just to give you some sense that there's a lot more being explored here and to be explored in black hole collisions, both observationally and by simulations. I told you that when a black hole spins, it drags space into whirling motion. I hang my wife up here, Carol Lee, above the north pole of the black hole. And if she has a gyroscope tied to her feet and one at her head, the gyroscope at her feet whirls around faster than that at her head due to inertia there, due to the dragging of space into motion. And so her head sees her feet going around counterclockwise. But if her feet look up at her head, they see her head going around counterclockwise. It's like taking a wet towel, you wring water out of the wet towel. Just think about it. If your left hand sees your right hand going counterclockwise, then your right hand will see your left hand going counterclockwise. So there's a counterclockwise twist in space at the North Pole and a clockwise twist in space at the South Pole. And these are what we call vortex lines, taking a phrase from fluid mechanics, that guide the twist of space. And I draw a vortex line for a counterclockwise twist of space, red, and for a clockwise, blue. So this gives you now some flavor of what we've learned from our SXS simulations and what we will observation with LIGO and LISA. And I'm going to give you that flavor by watching two black holes collide. This is from a computer simulation. This has the red vortex up, and that has the blue vortex up. Otherwise, they're identical, but they just have opposite polarity. And I'm going to remove the vortex lines and just color code the surface of the black hole, the horizon of the black hole, by the kind of vortex lines that are sticking out. It's clockwise or a counterclockwise twist of space. And so the two black holes collide and merge, and now we have 4 vortices of twisting space sticking out of this black hole. 2 came from each of the original black holes. The horizon of the black hole is shaped like a dumbbell. This is just paused momentarily to look at it. And it turns out black holes do not like to have 4 vortices. They only like to have 2 vortices maximum. And so these vortices fight with each other in a very interesting way. But the key thing is that they robustly retain their individuality. And so now let's watch the collision and watch what's going on. Here's a blue vortex in the upper right. Collided, merged. Now it's a red vortex in the upper right. Now it's blue. Now it's red. Those vortices fight with each other and exchange vorticity, exchange direction of twist. More precisely what's going on is once the black holes have merged, the vortex lines have reconnected themselves. The red vortex lines counterclockwise go out this red vortex on the horizon around and back into the red vortex on the back side of the horizon. Blue one comes out here. This is a blue vortex, goes back into the back side of the horizon. This is from the simulations. These are just stills from the simulations. And then every time this goes green, the vortex lines pop off of the black hole. They embrace each other and they create a ring around the black hole like a smoke ring that goes traveling out at the speed of light. And so you get smoke ring after smoke ring after smoke ring. As this ring goes off, it kicks back at the black hole and recreates an image of itself, but with reverse vorticity. And then as the second one goes off, it kicks back and creates rings with, again, reverse vorticity. It's an amazing process to watch on the computer. And then as these rings go traveling out of intertwined vortex lines of twisting space, their motion creates tendencies. These are things that stretch and squeeze. These are objects that live in the fabric of space that stretch and squeeze things. They are tidal forces. It's the same kind of stretch and squeeze caused by the moon pulling on the Earth's oceans to create the Earth's tides. Stretching Tendex lines going around this ring and squeezing Tendex lines going around the circumference of the ring. And this is a gravitational wave. And LIGO is designed to measure the tendencies that stretch and squeeze. It doesn't see the vortices. It doesn't have the technology to see the vortices. Now, this is far more complicated and far more interesting than anything I imagined was going on when we began doing these simulations. And it's really exciting to see this coming off of the simulations at the same time as we can then go and look at the shapes of the waves that are coming off and see that they agree, that LIGO detects, and see they agree perfectly to within the accuracy of the data, within the noise of the data, perfectly with the predicted shapes of the waves that are seen from the black hole collisions. This is just one very simple example. I want to conclude now with a few words about exploring the birth of the universe with gravitational waves, because this is what I believe is going to be the really exciting thing that's going on with gravitational wave astronomy, the most exciting thing within the next 20 years. And it's going to actually begin probably within the next 10 years. First of all, we have a hope of watching the birth of the fundamental forces of nature in the early universe. And I give you one example. When the universe was about 1/trillionth of a second old, the electromagnetic force and the weak magnetic force, which previously were unified to form what is called the electroweak force, they came apart, and the electromagnetic force, that is the electric force and the magnetic force, were created. They came to exist. And with them came to exist the Maxwell's equations that govern them. Previously, Maxwell's equations were not relevant to our universe. And there were no electric and magnetic fields. But they were created together, according to theory, at age 10 to the minus 12 seconds. If this happened in what is called a first-order phase transition, and there is reason to suspect it may not have been first order, we just don't know. But if it was first order, this is a technical phrase for the physicists and chemists in the audience and some engineers. If it was in a first-order phase transition, then the separate forces are born inside bubbles. It's rather like the formation of water droplets out of a water vapor. In the water droplets, the interior of the water droplets, you have an electric force and a magnetic force. Outside, you don't, between water droplets. But these water droplets then are predicted to expand very rapidly, collide, and in their collision, they produce a burst of gravitational waves, according to the theory. And this is all very strong, well-understood theory, except the issue of whether or not this was a first-order phase transition. Again, a technical phrase. These gravitational waves then, the wavelength of the waves was very short at that time, but it expanded as the universe expanded, so that today the prediction is that these gravitational waves are in the frequency range that LISA will be able to see. So one of LISA's primary goals is to look for gravitational waves from the birth of the electric and magnetic forces and fields. LIGO could see a similar phase transition, a change in the nature of the physical law, when the universe was 10 to the minus 22 seconds old, But current theory, as we now understand it, says that that was a desert. There was nothing interesting going on then, unfortunately. But of course, we don't know for sure. So LIGO is searching. Finally, if something had to come off the Big Bang in terms of gravitational waves, at an absolute minimum, there had to be fluctuations associated with quantum mechanics, just what are called quantum fluctuations of the gravitational field, because you can never get rid of those. And maybe there was something much more than that created in the Big Bang coming right off the earliest moments of the universe. But whatever came off of the earliest moments of the universe, the so-called Planck era, is predicted to have been amplified enormously by a process called inflation, an extremely rapid expansion of the universe, in the first roughly 10 to the minus 33, 10 to the minus 32 seconds of the life of the universe. Then these gravitational waves, even if you just began with vacuum fluctuations, you still get a rich spectrum of gravitational waves. They travel on as the universe expands and interacted, according to theory, with the electrons and protons in the hot plasma of the universe when the universe was 380,000 years old, and electrons and protons were combining onto each other to form neutral hydrogen, and allowing photons, electromagnetic waves, to propagate freely for the first time in the life of the universe. Those photons then, released suddenly from being trapped in the hot plasma, they will be affected in terms of their polarization by the gravitational waves that are stretching and squeezing the plasma as these photons are being released. And there is a prediction then that there should be a certain pattern of polarization put onto these cosmic microwaves, the so-called CMB, a polarization pattern that could be found today, and if it is seen and separated from any other causes of such polarization, that will give us evidence of the details of the birth of the universe and the inflationary expansion of the universe. And so the key point is that the gravitational wave spectrum that would be seen then in the polarization of the cosmic microwave background is, to use a technical phrase, a convolution or a combination of whatever came off the Big Bang and the influence of inflation. And so I envision that in the mid-2020s, say, when the data have been cleanly separated out, this polarization pattern has been found by a group called the BICEP collaboration, but it is mucked up with polarization that was created in other ways by emission from dust and what is called synchrotron radiation. And the challenge is to separate off that foreground noise from the observed from the polarization that comes from gravitational waves. I do expect that will be done successfully within years, not decades. And at that point, we will be using these gravitational waves to probe a convolution of inflation and whatever came off the Big Bang. And by 2050, there should be a successor mission to LISA in space that is looking directly at these same gravitational waves, but a very different period of oscillation, periods of seconds versus hundreds of millions of years for the CMB polarization. So by 2050, we may have observations of gravitational waves from the very birth of the universe convolved with inflation in two widely separated frequency bands. There is a prediction as to what that spectrum ought to look like. And having lived through a number of theorist predictions that were wrong during my career, I will hazard a prediction of my own that our predictions today are wrong, and that the struggle in the 2050s and maybe as early as the 2020s will be to understand what the heck is going on. Why is the pattern the spectrum not what we expect? And hopefully that struggle will help us to understand much better the Big Bang and the laws of physics that govern the Big Bang, the so-called laws of quantum gravity. So let me just conclude by saying it was just 400 years ago, approximately, that Galileo created modern electromagnetic astronomy by building a small optical telescope, turning it on the sky, and discovering the 4 moons of Jupiter, discovering the craters on our moon. It was about 2.5 years ago that LIGO gravity wave detectors turned on and saw gravitational waves from colliding black holes. Galileo opened electromagnetic astronomy. LIGO opened gravitational astronomy. There are only two kinds of waves that can propagate across the universe, bringing us information about what's very far away: gravitational and electromagnetic waves, and that's it, according to our current understanding of the laws of nature. So LIGO has done what Galileo did, and when you just look at the enormous changes in our understanding of the universe that have come from electromagnetic waves since the era of Galileo, I let you speculate what will happen over the next 400 years with gravitational waves and electromagnetic waves working together. Thank you.
Oh my goodness. So for you students out there, you can say you were there at the beginning of gravitational wave astronomy.
And you have the responsibility to carry this forward.
Yeah. All right, we have time for 2 questions. We're going to have one from downstairs and one from upstairs. How are we going to choose them, Tatiana? First, who's got the microphone? Do we have a student to ask a question? Right there, question.
So it seems like LIGO was detecting more gravitational wave incidences or black hole mergers than expected. So what does that mean for like how we see the universe differently?
So the number that, the rate at which the signal would come in was highly uncertain. We didn't know how far away the earliest signals would be because we just don't know how many pairs of black holes there are in the universe. And we didn't know by a factor of 10 how far away they would be. That means we didn't know the volume of the universe we would be searching by a factor of 1,000. So the signals were near the upper end of the range of uncertainty. So it was not terribly surprising. It was a little surprising that nature was that kind to us, but not terribly surprising. What was a bigger surprise was that the black holes were as heavy as they were. Because and theoretical work, simulations and pencil and paper calculations had suggested to astrophysicists that if you had a very heavy star that had the potential to collapse and form a very heavy black hole, there would be winds blown off the star that would blow away most of the mass of the star before the core collapsed. And so you would not get really heavy black holes. And so the mass of the black holes was a moderately big surprise. But, astrophysicists are good at explaining surprising results, usually, not always. So there are 2 explanations. Either these black holes formed when the universe was very young and there was almost nothing except hydrogen and helium in them. And so they had low opacity because there wasn't much else. And so they did not have strong winds. Or else these black holes were created when you made smaller black holes inside clusters of stars called globular clusters. The smaller black holes collided and merged and made bigger black holes, and the bigger black holes collided and merged and made bigger black holes. And this is basically in a chain. What we've seen is in a chain of those kinds of hierarchical collisions. So those are the 2 approaches, two theories at the present time for this surprising result. And that will get sorted out as we get more statistics on these black hole collisions.
Questions from upstairs? I see one back in the very, very back.
Boy, how can you see back there? I can't.
Only 67.
Yeah, I'm 10 years older than you are. No wonder. You're a young kid.
So for one of the slides, it was the birth of fundamental forces, and it said that the electromagnetic force and weak force came apart, gaining their own identities. What caused them to come apart?
The universe was cooling as it expanded. Whenever you have a gas that's hot and you expand it, it cools because it does work on the molecules do work on each other during the expansion in such a way as to make it cool. How do you explain that? Anyway, so anyway, the universe cools as it expands, and as it gets cooler and cooler, the fundamental laws change because there is, as I said, a phase transition. So at very high energies, the electroweak force dominates, and at lower energies or lower temperatures, the electromagnetic force, being separate from the weak force, dominates. So it's just because of the cooling of the universe as it expands.
So I'm going to use my deanly prerogative to ask,
Yeah.
you already talked about the surprise of the mass of the black holes. Is there a single biggest surprise, or is that it?
I think at the present time we have not had huge surprises. Okay. There will be, I'm sure, some very, very big surprises.
Quantum gravity?
Well, the thing I hinted at was that whatever came off the Big Bang will not be vacuum fluctuations. Right. And that will be because the laws of quantum gravity are doing something else in the Planck era. But that's a moderately wild speculation, but I think not extremely wild.
So let's thank Professor Horn for